Hello guys, hope you are doing well. I want to show uh, a research topic today, and I did this research using Python and Python Sumo and Tracy, the framework for in Python. So my research topic is adaptive traffic signal control using deep queue network. I do comparative study with rule-based method and I vary different headway patterns. Uh, if we look at the work plan of mine, I use Sumo and Tracy as a test bed and I consider a network. I'll show the network little bit later. The network is the the network is three four leg intersection, each located 600-meter apart, and three lanes for each eastbound and westbound approach, and three lanes in each north-south bound approaches. And north-south bound approaches are minor roads, minor arterials, and east and westbound approaches are major arterials. And if we look at, I use two competitive models. One is rule-based adaptive traffic signal control, and another one is DQ, that is deep queue learning based network, deep queue learning based network adaptive signal control. And I use 16 actually headway patterns. Those are divided into five groups. One is basic, number two is peak hours, extreme, realistic, and statistical. And within each five category, we have random, uniform, morning peak, evening peak, oversaturated, our urban arterials, bimodal, with different types of statistical headway patterns like log normal, gamma, Weibel, Erlog, and performance metrics I use to evaluate the performance of the two competitive models, the two competitive models uh, uh, under these 16 headway patterns. Those are average queue, average speed, travel time, delay, average delay, and throughputs. Now get into the next slide. Now I am talking about the simulation and performance evaluation. I divided into 9 steps. Step one, I generate traffic using different headway patterns. Then start Sumo simulation using Tracy, select, action, epsilon grid policy for DQN, and every simulation iterate every 5 seconds and calculate reward for traffic performance and store the experience in memory. Then collect performance metrics, lastly train DQN all, and also evaluate with respect to the rule-based method, and lastly analyze and compare results. And this is the road network. We can see that there are three intersections which are located 600-meter apart, and there are east and westbound approaches, and there are north and southbound approaches. North and southbound approaches are minor roads, east and westbound approaches are major roads. Next, I want to talk about the competitive models. First one is rule-based model. In the rule-based models, actually, the pseudocode is provided, and it consists with five components. One is monitor each intersection, compare approach demand, and apply extension logic. So how to compare the approach demand? We calculate the vehicle queues for main street and cross street to determine the current phase should extend or not, and extend green time 5 seconds if current approach is 20%, approach has 20% more vehicle competitive to other approaches, and it can maximum green up to 60 seconds. And there is overriding for coordination. If the phase is forced to terminate if during the last 10 seconds of 90-second cycle, if green wave need to provide the green wave offset. So I provide the green wave offset and consider the queue length and extend green times to provide the rule-based adaptive signal. And default switching system is green, yellow, and next green or red in the same phase. And I use extension, green extension for the rule-based adaptive signal. This is the policy for my rule-based system. This is the baseline I use. Next, and if we look at the rule-based method, we can see that the firstly Q data is collected, then Q is comparison, then green extension is provided. If required, then constraint are checked. If there are minimum green or maximum green, there yellow interval is provided, then provide coordination if there are any chance to provide the green waves, and lastly force to phase change. And this is the frame structure for the adaptive signal, rule-based adaptive signal. Next, I use the most important models, that is DQN adaptive signal. In this signal is also consist with 5 steps. One is state extraction, is convert the traffic data into queue speed and waiting time of 636 vectors. Then epsilon greedy policy is taken and exploit Q values from the new Q value action from neural network, and our reward is calculated and weighted are given for Q reduction, speed and throughput. For Q reduction -5, speed +4 and throughput +0.1 to prevent the gaming. Then store the experience in memory, and random batches are trained and breaking temporal correlation. And lastly, train policy are implemented in the model to use the DQ and adaptive signals. And this is the frame structure. If we looked at the first traffic data are collected, then state representations. I use the dueling DQN architecture. Action are selected, reward are calculation, experience are repay, and lastly, the adaptive signal timing is adjusted accordingly. And the thing I talk about the headway patterns. We use the 5 types of headway patterns. First one is basic, which has uniform, platoon, and random type. And platoon arrival are 0.8 to 1.5 second headways with 3 to 6 second gaps. Peak hour patterns, we have different 2 peaks. Extreme condition, we have saturated, free flow, and mixed fleet. For extreme conditions, especially for the mixed fleet, there are 90% cars uh, with headway 1.5 to 3 seconds, and 10% trucks have headway of 3 to 5 seconds. A statistical distribution like log normal, that is positive skewed gamma, flexible shape parameters with 0.2 Google and air long distribution are also considered. And for real world pattern, urban arterial, highway march incident, that is disturb the flow by 1.2 second headway in the middle third as provided, or bimodal distribution is provided. And all 16 headways traffic is generated using tracing. The performance metrics I use are 5. Those are average queue length, average speed, then travel time, delays, and throughputs. And average travel time is calculated using the exit time minus entry time. And if we look at the delay is calculated actual travel time minus free-fall travel time. And I consider the free-fall travel time is the route length divided by 50 kilometer per hour speed, which is corresponding to 13.89 meter per second. And throughput is the total number of vehicle journey to exit the network is converted into hourly metric. And this is the 16 headway pattern that I use. Those those headway arrival distribution patterns are provided here, and they are graphical representation, you can see. And from the headway comparison, we can see that for the two competitive models, there are 16 headway patterns and 5 performance metrics. So 16 into 5, total 90 parameters, actually 90 combinations. And within that 90 combinations, that our TQN model outperforms the baseline adaptive signal most of times. And we can see that for uniform distribution, uh, the headway patterns are, are headway patterns are 6.02 second, and similarly average headway for bimodal is 3.02 second. I am actually providing the headway patterns distribution, and in the right side, top right side, we can see that the headway pattern distribution in the box plot, and the left below we can see that the traffic variability pattern in the 16 headway models, and I provide mean, max, standard deviation, median headways for each of the models. Next, this is the headway. If we plot first 200 vehicles in the headway patterns, we can see the headway patterns will be like this. We can see uniform, oversaturated, Weevil distribution, bimodal, incident-induced or disrupted flow traffic headway time series. And if we look at that I am talking about the improvement policies metrics that taken, we have 5 criteria: queue, speed, travel time, delay, and throughput. And within all these, we can see that the only uniform distribution headways, the speed is little bit lower. Otherwise, in all cases, our DQN model outperform the rule-based model. We can see that especially if we look at the travel time, platoon, urban arterial, log normal, random, mixed fleet, incident, in all cases, the percent improvement is more than 60%. And if we look at the queue length, almost all cases is more than 50% improvement for queue length. Similarly, for delay, we have almost 50% delay improvement for all cases. For throughput, we can see that the urban arterial and platoon Headway has the most improvement using DQN adaptive signal compared to the rule-based model. And if we look at the improvement heat map, we can see that the bimodal, along evening peak, free flow, all these headway patterns have good percent improvement uh, in delay. However, for speed, the improvement is close to 20 speed improvement, and throughput improvement is close to from 60 to 30, even 20 some cases. The most improvement we can observe in case of delay and queue length, and also in the travel time we can see that there are good percentage of improvement. And if we compare the baseline adaptive signal with DQN, we can see that the queue length and the DQN for speed, travel time, delay, and throughput, we can see all these five criteria and total 16 headway patterns. Their improvement or improvement in the models over the baseline model if we consider the DQN adaptive signal. And if we look at the radar chart, I plot using the 5 patterns, most improved pattern, urban arterial. It is provided one of the best. Then platoon and log normal is also good. Airlong and random headway pattern, it provides a good result. And this is the radar chart we can see. using the five top patterns, those are most improved using DQN over the rule-based model. And if we look at the metric relationship, the queue length versus delay, speed versus travel time, throughput versus delay, and queue length versus throughput, we can see the corresponding uh, relationship and graph. We can see over here under 16 headway patterns. And this is all for baseline actually, for baseline adaptive signals. And even we can draw it for the adaptive signals. We can draw it for the DQ and adaptive signals as well. And this is the improvement distribution. We can see that the Q length has the most improvement. Delay has improvement with less uh, less spreading. The speed has the lesser improvement in the DQN model compared to the rule-based adaptive signal. Throughput has also some improvement. We can see also travel time we can see. And this is the top 10 and bottom improvement. We can see top 10 improvement and bottom 10 improvement. We can see the pairs and their percent improvement. And top 10 improvements all are in delay, and bottom 10 are most of cases, those are in case of speed. And if we look at the DQN performance, I have provided the heat map, one thing, and then provide the average improvement by matrix, top 10 pattern by average improvement, and improvement by distribution is also provided. And lastly, there are also metric, correlation metric is also provided. We can see the correlation metric for improvement, percent improvement is also provided. And GitHub code is provided in the link as shown below. You can use and reproduce the result. And I will also input the video presentation link after uploaded in the YouTube. Thank you so much for the presentation.